Yes, I'm Nahravan, and I work at Aarhus University as a postdoctoral researcher. Uh, Today, I want to talk about two fluid model operation simulation of CO2 ejector, project that I work with Negar Alvanifar, my colleague, and our supervisor, Priya Furuli. So first, I will talk about CO2 heat pump and ejector. Then I will touch on the available numerical approaches and how we are going to assess the solver that we chose for this problem, and in the end, concluding remarks. So, schematic of the problem. Uh, on top, you can see the components of the heat pump and the cycle. So, in conventional cycles, when the fluid comes out of a condenser at a high pressure and temperature, it goes through a expansion valve, and the pressure drops to the level of the evaporator. Here, we do the same thing with the ejector, but with the difference that the ejector is capable of recovering a part of the expansion work and improving the overall performance of the cycle. So what happens in the ejector is that the flow goes through a converging nozzle, and in this nozzle the pressure drops, and the flow is accelerated to the speed of sound at the throat, where we have where it experiences choking. After that, the flow is choked, it accelerates further, and the pressure drops in the expansion part. And here, the flow will be supersonic. And the pressure at this point is below the pressure of the evaporator. Here we are at 0.3, and evaporator is at 0.10. And because of the lower pressure, it can draw the flow from evaporator. So the first flow is called motive flow. The second one is secondary or suction flow. The two flow mix, and in the end in the end of mixing session, it reaches state 4. Now it's time for another expansion, where the recovery of the expansion work happens. So in the diffuser, the pressure increases to 0.5, and here is where where ejector is superior to the conventional expansion valve. But it brings a couple of challenges. So we have supersonic flow with shock waves, rapid phase change from 0.1 to 0.3, and operation in supercritical region. CO2 operates in supercritical region. It makes it hard to calculate the phase change and the properties in this region. And coexistence of condensation and evaporation. In the suction, we have condensation, and in multi-nozzle we normally have evaporation, and in the mixing session both. It's a very complicated problem to simulate, and besides that, the experiment is also challenging. So why do we want to do this study? There has been a couple of numerous studies on this topic. It's not new, but still they lack detail. They cannot provide enough detail from the flow. They have a large error in prediction of the overall parameter. And the reason is that the numerical method that they are using is not sophisticated. And the experiments also cannot give us any detail. It's mostly the overall performance parameters. And all of those details are important to improve the performance of the ejector and COP of the whole cycle. So what are the numerical approaches in the literature? They're mostly focused on homogeneous, equilibrium model, and mixture model. Both use both share general concept. The fluid can be considered as a mixture. So if we write down mass, momentum, and energy conservation equations, they are pretty similar, but mixture model can handle phase interaction, like momentum transfer, heat transfer, and mass transfer. But homogeneous equilibrium models, as the name suggests, it doesn't consider these parameters. So this characteristics lies in the way that they treat volume fraction. HEM, volume fraction is extracted from equation of a state, and in a mixture model, each phase is tracked through solving equation for volume fraction. So we know where we have vapor, where we have liquid, and using that distribution, we can define mixture properties. Again, for mixture properties, HEM just reads the table of properties, but in mixture, we know alpha, and through alpha, we can calculate the mixture property. So alpha is multiplied by the property of liquid, and then 1 minus alpha L, there's a typo here, is multiplied by vapor property. And the properties of liquid and vapor is read from equation of a state. That's a huge difference here. So what are the pros and cons of each method? Both are quite simple and well established, so anyone can access to it through commercial softwares or open source softwares like OpenFOAM, and there are a number of literature that give you enough details to do the simulations. HEM is more straightforward. It has lower computational costs, but it considers continuous velocity, which is not true here in these simulations, and continuous temperature fields. Those rapid phase changes that cannot be simulated through equilibrium assumption. In the literature, they try to modify it and add some models to include the relaxation, but still not a reliable method. So, and in the end, as you can say, it doesn't have enough accuracy. Mixture model, on the other hand, can consider models for heat and mass transfer, and it gives better results, but still it relies on empirical correlations, and it's not versatile enough. So even in prediction of overall parameters, it has large errors, from 10 to 20%. And when it has such a large error in predicting the overall parameter, it cannot be trusted for local phenomena, which is why we decided to use two-fluid model. There is no comprehensive literature on this method. It solves mass, momentum, and energy equation for each phase separately. That's why it can, we expect it to resolve our problem much better than the two other methods. So the red expressions that you see here, we need closure models for them. And these closure models are quite a lot. Like, you need model for distribution of the phases. You may have bubbles, droplets, and then you need to assume when vapor or gas or liquid is continuous, when it's not, and then heat transfer coefficient, visual mass, wall lubrication, lift, and turbulent dispersion. So all these models gives us a lot of leverage to reach a more realistic result. So I almost covered this part. So what are the main challenges then? One of them is equation of state. I will tell you more about the equation of the state later. And the lack of data on phase interaction that we want to handle through closure models. This is quite huge and can really deviate. It can cause a huge deviation from the physical results. So it should be handled very carefully and delicately. So the solver that we use is multi-phase Euler form in OpenFOAM 10 from Foundation. And since there is no detailed experiment from CO2 ejector, we broke down the problem to different parts. One, to check the shock capturing capabilities through air ejector test case, then compressible flow with multi-phase with phase change through steam nozzle test case, and then we check real properties of CO2 through knuckle oven nozzle, which is much less complicated compared to CO2 ejector or even other test cases. And the last step would be simulation of CO2 ejector. So this is simulations of air ejector. One sample on top, you can see the experiment compared to blast foam, and on the bottom, experiment compared to multi-phase Euler foam. Why blast foam? Blast foam uses Riemann solvers, and it's better solver compared to other solvers that are available in the official results of OpenFOAM. And as you can see, it captures the shocks quite sharply, but multi-phase Euler foam smears the shock a little bit. Still, for a problem, it's a reasonable result, and surprisingly, it's predicting the location of the waves more accurately compared to blast foam. So we are satisfied with this performance of the solver in single phase, and we moved on to simulation of converging diverging steam nozzle. The test case that you are seeing here is from BNL lab. It's very well-established benchmark, and there are tons of test cases that we could play around with them and verify the solver. One is shown here, and the solver predicts the distribution of volume fraction along the nozzle very well, and the same is about the pressure and other variables. So it wasn't actually that easy to reach these results, but it was a very good playground for us to see those closure models in the solver, how we should handle them, how they affect the results. And then the main challenge, which is equation of SA finding the properties, because so CO2 is not like water or air. The equation of a state is not straightforward. It is governed by Span-Wagner. It is the most accurate equation of state out there, but it requires a numerical solution, and it's computationally expensive. So it's not feasible to solve this during a CFD simulation, which is why we create a table of properties. This is a common approach among literature. Though two solvers are available, ref probe and cool probe. So we take the properties from these two sources. One of these two, we are using cool probe, but both are common. And we create a table of properties based on pressure and temperature. OpenFOAM takes uniform distribution of pressure and temperature. And from this, it interpolates the properties in the points that are not available for it. So in the figures, you're seeing pressure versus temperature, and pressure versus enthalpy as an example of the effect of pressure, temperature, uniform distribution on different parameters. So red is vapor, blue is subcooled liquid. Here is supercritical. Supercritical, we don't have a distinct phase, and that's a huge problem. So we need, but the solver doesn't know about that. We have to define liquid and vapor. So define this region to be liquid and this region to be gas. And then for different purposes, we have different distribution, of course, but the thing that they have, most of them have in common, is that close to the critical region, the change in the properties is pretty sharp. So no matter how much you refine, you will see that here the accuracy is pretty low. And there is another problem. What OpenFOAM solves is pressure and enthalpy. There is no guarantee that this enthalpy falls. For example, if we are calculating gas properties, falls in this region. It may fall in somewhere that nothing is defined. And then we have a big problem. And OpenFOAM cannot handle it. We need to code it ourselves. So to solve these issues, first we want to add table with local refinements. And next is to map values from vapor liquid boundary to states where vapor and liquid doesn't exist. And by that I mean here. And to do this, we need to modify term physical properties, term physical library of OpenFOAM a little bit. For now, we just use a bit of extrapolation here just to see how it performs. So Nakagawa nozzle is the first test case that we used to see if the solver can handle this kind of tables and is it stable or not. It wasn't in the beginning. It had many problems. We needed to do a bit of smoothing. But in the end, it worked fine, at least for subcritical state. And you can see that the result well matches the experimental results for pressure and temperature. But this one is for subcritical. For supercritical, we still have problem. That region is not easy at all. And then we check CO2 ejector. So the result that we are seeing here is not physical. We just wanted to see if table of properties that we made for subcritical region works for CO2 ejector or not. And at least we were satisfied that we could run the solver and it could converge. But we need to wait for the proper table of properties to run the test cases and validate them with the experiment, with the results that we have from our industrial partners. So to summarize, the numerical literature lack enough accuracy that is required for design of CO2 ejectors. Two-fluid model could be promising. It is very complicated if you look into the solver. In OpenFOAM is a huge solver, many models, many submodels. And it's very delicate dealing with this solver. So even though it gives us a lot of leverage, at the same time it's a bit dangerous and it can deviate. So multi-phase Euler foam, we checked it can well handle the compressor waves to the accuracy that we need, and it can handle phase change due to flashing. We checked this through the steam nozzle test case. And so for CO2 EOS, OpenFOAM tools are not enough for us. We need to modify it. And the next step, of course, is to modify the table of properties in OpenFOAM to add a bit mapping of those values that it doesn't have to the boundary of vapor liquid. In subcritical, it means the saturation curve, and then validate the CO2 nozzle test cases. There are nozzle test cases that tells us about volume fraction, and volume fraction is the most challenging parameter to resolve. Pressure normally works fine, but volume fraction is very challenging. And in the end, we will simulate CO2 ejector. Thanks for your attention.
Yeah, good work.
Thank you.
I just have a small question. In page 9.
9.
Maybe I missed something because really I'm wondering how did you calculate the mass generation rate? Because the results are, numerical results are quite good.
Yeah, it's yeah. So we tested different kind of nucleations. This one is a wall nucleation.
Yeah, because in your models, maybe I missed how did you calculate the mass, the vapor generation rate?
Okay, so wall nucleation. So we on the wall, we inject wall nucleation. Yes, on the wall we inject bubbles, and so here you see that the pressure drops, and at this point, it enhances the phase change. So we inject the bubbles all through the nozzles. Here they cannot grow; they're eliminated. But here, because of the low pressure, the bubbles grow and convect downstream.
You also modeled the bubble growth?
Yes. We use a population balance model. So okay. Population balance, we give a distribution of diameters, bubble diameters. And so initially we give, through the volume calculation, we give an initial size of the bubble. It is injected. And then this bubble, if there is a possibility of growth, which means heat transfer with surrounding flow, it starts to grow. And then if it is large enough, it is transferred to another, this population balance, they have different groups, like group size to X, size X to Y, then Y to Z. And it is moved to another size. And then depending on the size of the bubble, it may be transferred to the mainstream. It may go closer to the wall.
Music.
Pardon?
Because you mentioned this breakup and coalescence.
Yes, they are all they can be simulated. And OpenFOAM has it. I mean, I'm just using it.
Okay, thanks.
Yeah.
Okay, one more quick question from audience. I have a quick question about the phase change process. So, do you have the phase change model in your two-fluid method?
Yeah. Yes. So there are many parameters actually. So a huge part of the solver is just designed to handle phase change, and okay, I'm not sure how can I elaborate this, but the quick question is yes. Yeah. Okay. So you give the solver a heat transfer coefficient, heat transfer model, or you can consider different species. So it can handle phase change through two different methods. One is through heat transfer with the surrounding, and the other one is through the mass transfer of species through the interface. It can consider both. Depends on your type of problem. Like for example, for cavitation, the species could be species transfer through the interface could be a good choice. And so the input of the solver on tutorial level is that you choose in the beginning which model you want to use. You can't even turn off the phase change totally and just run the solver without any phase change. But yeah.
Okay.